Hey everybody, welcome back to another fun and exciting Algebra 2 class. Today we are going to jump into lesson 7.6. It is the final lesson in this chapter, and the lesson is about, it's kind of a little bit more of a complex lesson. Really, this borders on pre-calculus, so I'm not going to go really in depth into this lesson because pre-calculus is going to take you here. What I want to do today is lay the groundwork for you so that you can understand the concepts when you do get to pre-calculus. Okay, so what does that all mean? Well, open your book to lesson 7.6. It is on page 359. 359. All right, so what's going on here? Application of exponential and logarithmic functions. A lot of times we think to ourselves, or maybe we even say out loud, when am I ever going to use this stuff, Mr. Steve? I don't know when I'm ever going to use this stuff. Okay, well, here's an example. And here's the thing that you don't like about math. I've been teaching long enough. I know this. Here's the thing that you don't like about math. You don't like the story problems. In other words, you don't like it when we actually use it. And you're like, wait a second. It's true. Students always want to know, when are we going to use this? And then when we find out how to use it, nobody likes it. Okay? So don't ask the question if you don't want to know. But this is a place that we use it. Now, let's talk about some of this stuff. This is actually kind of in the middle of the news right now. We're still kind of in the middle of the pandemic, the COVID-19 coronavirus pandemic, and going through vaccinations and going through different things with that. Well, before the thing even kind of got out of control, we knew, mathematicians, scientists, they knew what it was going to look like. They knew how it was going to go up. How did they know that? Well, in the very early stages of a pandemic, you can look at the numbers, you can look at the statistics, and you can put them into an exponential function. I was watching a video of a man, and this was, let's see, I think it was March of 2020, okay? So the pandemic was still really fresh, brand new, and he took all the data that he had, and I think it was like March 10th he made the video. And he said he predicted on this date, and he named a date. I want to say it was like April 16th or something, whatever the date was. He said, we will reach 1 million cases worldwide. He was off by 1 day. He missed it by 1 day. In other words, he projected what was going to happen. He said, hey, in a month from now or in 6 weeks from now, we're going to be at this number of cases. How did he do that? He used math, okay, and he used the application of exponential and logarithmic functions. If you go to websites and you look up coronavirus stats or whatever pandemic you want to look at back in history or even in the future if we have another one, you will be able to see the numbers, and the numbers always hold true. What are the numbers? How do they get the numbers? They get the numbers through mathematics, through statistics, through applications of exponential and logarithmic functions. There's so many other things that we can use this in: population growth and investment when your money is compounding and the interest is compounding. Just a number of different things. I mean, literally thousands. Businesses use this all the time to project product and to order product and to do different things like that. So businesses, banks, governments, you name it, they use this stuff. This is real math, and it's math that actually works in the real world. Okay? All right, that was a big intro, and so let's just jump into it. Really, most of this lesson is intro. So look down at the screen and down in your book, either one, page 359 again in your book. Exponential growth rate. What is this? This is the change between the function as the x value increases. So in other words, as we say, okay, x equals 4. Okay? When you do your exponential, when you figure out your solution, you get an answer. And then when x equals 5, and then when x equals 6, and then when x equals 7, and you keep changing the value, you'll see there's a chart in your book where they keep changing the value and the output keeps changing. What is this change called? Well, in math, we use a little triangle right there. You'll see it. Now, that little triangle is not literally a triangle. It's actually a delta. Okay, I'll write that down, delta. And delta is a Greek letter, okay? It's alpha, beta, gamma, delta, I think. I took Greek in college, believe it or not, so I'm pretty sure that's right. It's been many, many years ago that I took Greek, and I wasn't very good at it. But I think it's the fourth Greek letter. Did you know that pi, pi, is a Greek letter? Okay, so this is just the delta. We use this. Oh, the E that we've been using is also a Greek letter, epsilon. And so math uses a lot of Greek letters, and so this is just another Greek letter, but this is the delta. It looks just like a little triangle. That is what they use to signify the change in the output of a function. In other words, when the output gives you an answer. Okay, so when you solve the function and it gives you an answer, the change between the two, so in essence from x equals 1 to x equals 2, whatever that change in the function is, maybe it's 0.025. Well, that 0.025 would be the delta. It's the change. So between every time you change the function, whatever that delta change is, they signify that with the little triangle. Again, we're just laying the groundwork. I'm not going through a lot of these right now. I'm not showing you a lot of these right now. We will do these in pre-calculus. Okay, but this is something that's kind of preparing you, your understanding for pre-calculus. All right, there's two different types of function data. There's what's called continuous function data, and this is on the next page. You can go ahead and turn your books over to page 360, and you'll see down there at the bottom, there's continuous data. What does that mean? That means when something is measured or weighed. For example, any value is acceptable. You could have, I put down there 5.876 pounds. Well, that you weighed something and then you didn't round it off. Maybe you rounded it off to here, but you didn't really round it. You didn't round it off to a whole number. You still have a fractional number or a decimal number. You can have really any type of number. Continuous is just anything that's measured or weighed. Okay, the height, how much does something weigh, the liters that you can pour into something, that's called continuous. The second type is called discrete. In discrete, only whole numbers, counting numbers, are acceptable. For example, if you get the answer 11.22, that's not an acceptable output. You would have to round that off to 11. This is when you have so people are not measured and people are not weighed. Now you can weigh a person, but like in the population, when we measure or weigh, we don't measure or weigh the population. We count the population. So if you do your thing and you get there are 1.76 million people, okay, fine. But you can't say there are 73.2 people. That doesn't work. Why not? Because you can't have 0.2 of a person. So what do you do with that? You just say 73. You round it off. Now, sometimes you have to round up to the nearest whole number. For example, if you're talking about people, maybe you would say anything after 73 becomes 74 because you'd have to round up. It depends on what your criteria is for your search or for your data. Okay. All right. Next, let's talk about how are we going to use this most? Just normal people, okay? You and me, normal people. How are we going to use this? We're not mathematicians. I'm just a school teacher and you're just a student. So how are we going to use this? Well, everybody likes money, right? I know, yeah, everybody likes money. Sure, you got to have money to live. So what about when you invest money or when you borrow money? Everybody's probably going to do one of those two things in your lifetime. You're going to either borrow money from somebody or you're going to invest money somewhere, okay? So we need to understand this so that we can understand Now, back in the day, like 100 years ago or more, everybody used what's called simple interest. Simple interest is just that. It's simple. You just take interest equals principal times rate times time, and we've done that before in past math classes. We're not really going to spend a lot of time on that because it's just a multiplication problem. The next one is what's called compound interest. Compound interest. And if you're following along in your book, this is on page 361. Page 361. And compound interest looks like this. A equals P times, and that's principal, by the way, plus, parentheses 1 plus R over R is rate, N is the number, over NT. Okay, and we'll get into what all that T is time, by the way. So principal, rate, and time, I equals PRT. And so we'll get into what all those different pieces mean to that in just a second, because we're going to do one of these here in just a sec. The next one is compounded continuously. And now this one's interesting because this one's actually one that we're using right now because we've been using the E in the calculator. What does that mean? Okay, that's Euler's number, so don't forget about Euler's number. Here's an application. Some of you have been thinking, why am I learning about Euler's number? Because we use it. And here's a place that we use it. We use it with interest that's compounded continuously. And what we do is we get A equals P. And then instead of this part, what we're going to do is we're going to use Euler's number. So P times E to the RT, rate times time. So this one is principal times rate times time, but it's a little different. What's going on here? It's not times. These are exponential, and then we're using Euler's number. So we're using all these different things that we've been learning in that one. All right, so let's do one. Let's do a problem. Let's pretend like we're going to go to the bank and we have $1,500 in our account, and we want to invest that in something. Maybe it's a stock or a bond, or maybe it's just a savings account that earns 6% annual interest. And we're going to do that for 18 months. Now, this is important to know that time is always, T is always in years. Okay? So 18 months would just be T equals 18 over 12. And that's important because it's not 18. You don't multiply by 18. You multiply by 18 over 12. And that can reduce out to 1.5. So that's 1.5 years. Okay, so 1.5. And again, that's very important for this problem. So let's go back and let's erase that. And let me put in there. So I'm going to cross off the 18 months, and I'm going to put 1.5 years because we're going to use 1.5 years. All right, so the first one is I equals PRT. Okay, and so we're just going to multiply out. This is the principal because that's how much you put in. This is the rate, and this is the time. So I equals P, 1,500 times rate, 0.06, because we have to move the decimal point 2 places, times 1.5. Okay, let's get our calculator out and do it there. So 1,500 times 0.06 times 1.5 equals. We're going to make $135 in simple interest. 135, and that's called simple. All right, so I kind of jumped ahead a little bit and I wrote out the formula. I just plugged everything in. So let's talk about this real quick. There's the P, okay, for the principal. Here's just part of the formula. Okay, so that's the 1 plus, and then R over N. R is the rate, that's the 6% over 1. What's the 1? Well, in this case, we're just doing it for 1 year, the number of payments or the number of payouts, if you will. And then R and then T. So R is 1 again because, NT. N is the number of payments, and then the T is the time. The time was 1.5 years, okay? And so now we're just going to plug that all into our calculator. Make sure that you have a scientific calculator for this and use the parentheses where they go. Okay, so let's take out the calculator and let's do this. My calculator doesn't work all that well, so I have to do this 1 plus 0.06 over 1 first, and then I'll write that down. You just add this up and you get 1 plus, and then I have to do parentheses 0.06 divided by 1, close the parenthesis, equals 1.6, 1.06. 1.06. So now I want to take that, I can multiply that together just in my head, 1 times anything times a 1.5, and then I'm going to multiply by 1,500. So go back to the calculator, and so we're going to raise this to the 1.5 power, and that equals 1.9, and then we're going to multiply that times 1,500. That's going to give us $1,637. So 1637. So 1637. And that's compound. Okay, you see a difference right here, right? So you see where the compound is a big number and the simple is a small number. Well, what I did not do with the simple is I didn't add it back to the 1500. That formula adds it back to the 1500. So really what I'm going to get here is if I add it back to the 15, I'm going to get 1,635. So now the bank only made an extra $2 there, right? But now think about this. For you, well, actually, this is an investment, so you made an extra $2. But let's pretend like this is you borrowed this money. Well, the bank made an extra $2. If the bank makes an extra $2 on every single person, then pretty soon they make a bunch more money. So it's a little trick that they have that they get more money out of you when you borrow money. They use compound, or they also use continuous. So we're going to take now P to the ERT. That kind of looks like PERT right there, okay? So we're going to take P to the ERT. All right, so what's the P? That's 1,000. We'll go back to that. All right, so let's fill in this formula. What is the P? The P is the 1,500. That's the principal that we invested. What's the E? That's Euler's number. What's the R? That's our rate, 0.06, and then times our time, which was 1.5. Now we'll just plug that into my calculator. My calculator is going to work just a little bit differently here. I need to do the exponent first because I can't raise it to the E on this calculator. So let's go ahead and do that. 0.06 times 1.5 equals 0.09. So now that becomes 0.09. Okay, so what we'll do now is we'll take Euler's number and we'll raise it to the 0.09. And that's going to give us 1.09417. And then we're going to take that and we're going to multiply it times the principal, the 1,500. And that's going to equal 1,641, 1641. 1641, and that's continuous. Okay? All right, so you can see that every time we did this, the bank, if we borrow money, the bank is making more money. If we invested the money, we're making more money. So that's how that works. That's how interest works. Nobody uses this first one anymore. Everybody uses one of these two. Why? Because they make more money. That's all there is to it, okay? Make sure that you go back and rewind that and take a look at it if you didn't figure out one of the things that I said, if you don't understand it. You will have to know how to do this in real life and maybe on a quiz or a test coming up, okay? So work hard, try to understand that. It's just plugging into a formula. Make sure you know how to push the buttons on your calculators, okay? All right, that's all I got for you today. You have a good one. Bye-bye.